preview. It's fine. Okay. All right. Make sure that you got your handout close by. I'll be giving you the page numbers as we're going along. Make sure that you got your handout close by. I'll be giving the page numbers as we're going along. Okay, we're live on Facebook as well. Finally, I got to pull through. Welcome everyone again. We are doing chemical equilibrium. My name is Kalani Jovin. I know it's not all of you who are here from Star School. Some of you are, some are coming from different places. We all welcome you and that's okay. All right. If you want to say something, ask something, it's okay. You can always lift up your hand using the platform. It's very easy. Under almost close to participants, right? There's a part where if you click onto it, it's supposed to be 3 dots if you're using a phone, more if you are using a laptop or a tablet. And then from there on, you can be able to just raise up your hand and I can see you from the side and I can unmute you. Please ask me as many questions as you possibly can. All of you are currently muted, so even if you try to unmute yourself, you can't. I've just made sure that the settings are like that. By all means, make sure you are muted like that. Whenever I decide to unmute you, it will be okay, and we'll take it up from there. It's 3:01. Let's begin our lesson. We'll start off with our handout, and we'll go to a question. In fact, let's do this before the handout. I want to do a question before the handout. There's a question that I want before the handout, and I think it's on, if you have the Star School book, those that have the Star School book like me, like this one here, for the Star School book, let me give you the page number. If not, I'll just float in the handout as it is. Page 143, Star School book, page 143 is 2010 March, paper 2, question 8.5. Those that don't have the handout or that don't have the book from Star School, here is everything. All right, it's the same thing. Let me just float it here. It's a 2010 paper. Let me just look for it for you. It's a very interesting question to start with because it's not your normal questions as it were. And I want to make sure that everyone understands what I'm going to do right now. So Star School page 143, can somebody write all this information on the chat so that at least those that are coming in don't have to ask what we're doing. Page 143, 2010 March, paper 2, question 8.5. Page 143, 2010 March, paper 2. Okay, somebody help me with writing that. That would be much appreciated. Okay, I'm just gonna float it in now on the screen. I'm gonna share the screen and we begin doing that question right there. Okay, there we go. Okay. I'm sharing the screen. Just want to make sure that everyone is pretty much clear. On the Star School book, thank you so much. I saw someone putting that right there so that everyone is pretty much clear on what we are doing. All right. There. 2010 March, paper 2, question 8.5. That is what we're going to do. Guys, my internet is unstable. Let me know again if you can't see anything. We'll take it up from there. Let's start off with the question. I'm just trying to float it here for those that don't have it. Just trying to float it. If I pull through. Can you guys hear me? Somebody's saying I disabled my audio because I didn't. Okay, give me a heads up, especially those that are on the video. Can you hear me? Just give me a shout if you can hear me. Great, lovely. People can hear me. Okay. All right, thank you. Those that can't see anything, keep moving your slide, your phone. You will be able to eventually see me, right? Avoid looking at the people. Look at me. Avoid looking at the people. Look at me. Should be able Okay. Hi. Can you hear me now? Can you hear me now? Yes, finally. Okay, let's try that again. All right. I'm trying to share the screen and it's disabling me big time. All right. Devil is a liar. The devil is a liar. Okay, let's see this. Okay. All right. Let me stop this sharing here because I'm not winning with all of this. Oh, come on, man. Let me stop sharing, start from scratch. How's this? Okay. Tell me if you can see the screen because it says I've shared here. All right. I think I see it now. Okay. Beautiful. It's the 2010 paper. There we have it. Let's start there, guys. Sorry about the delay. It was a bit of a mishap on my part and also the internet that I'm currently using. Okay. This is a handout, but all these things you have in the book and Star Schools. Those that don't have this handout, don't worry. I'm just going to pick out just one question here. Then I'll go to the handout that I sent on WhatsApp. I did not send this one. I did not send this one on WhatsApp. I only sent the other one. So right now I'm using a different one. Let's start. 8.52, 2 moles of nitrogen dioxide, NO2, and an unknown amount of nitrogen tetraoxide are sealed in 2 decimeter cubed container that is fitted with the plunger at a certain temperature. Okay, so that's what's happening. The following reaction takes place. As you can see, everyone is a gas right here in this particular moment. So it's 2 moles of nitrogen dioxide reacting to give 1 mole of nitrogen tetraoxide. At equilibrium, it is found that the nitrogen dioxide concentration is 0.4 moles per decimeter cubed. The Kc, equilibrium constant at this temperature, is 2. The first question is 9 marks. It's obviously something to do with Kc or a calculation. 8.51. Calculate the initial amount in moles of nitrogen tetraoxide that was sealed in the container. That's what they're asking us to do. The initial amount of nitrogen tetraoxide that was sealed in the container. All right, sharp. That's our question. Keep that in mind. All right, and then I'm going to try to do it now with you. The first most important thing, my people, is to be able to understand what is being asked, and then to be able to draw the table, and the table method will be the one that probably I would use right now, which is pretty much straightforward. But what's interesting about this question and why I chose it is because of the fact that there is an unknown amount of nitrogen tetraoxide. In other words, the nitrogen tetraoxide in the beginning is not 0. The product is not 0. It's already there. And that's why I chose this question, so that you can understand that in such a case where they talk about the nitrogen tetraoxide having an unknown amount, it's there already. Okay, let's begin our question. We're going to do 9 marks right now. Let's go. As obviously, we start off with the molar ratio. So I'll write molar ratio right here. Then it's moles at start. So moles at start right there. Okay, right. Then it's going to be moles used or produced. So moles used or produced. Then I'm going to have moles at equilibrium. There you are. Then I'm going to have finally concentration at equilibrium. All right, let's do this question together. I'm just going to be doing this, and this will become my particular table. There you are, and there you are. Okay, So what's happening currently here? We're looking for the initial number of moles of nitrogen tetraoxide, N2O4, the initial number of moles of N2O4. So in this case, you only have 2, and I'm just going to write them at the top here. You've got NO2, there you are, and then you've got N2O4. Okay, let me start off with the molar ratio. Let me use a different color. The molar ratio, as can be seen right here, is 2:1. 2:1, that's the molar ratio. Now, the moles at start, if you go to your question 8.5.2, it says to me here, okay, people are sending messages. I don't know what's going on. Can people hear me? All right, okay, everyone in the meeting, right, I'll send the question right now on WhatsApp, okay? Allow me to just do this one here. I'll send the question on WhatsApp. Now, the question says, initially at start, you had 2 moles of nitrogen dioxide, but you had an unknown amount of nitrogen tetraoxide. Usually, in all the questions that we do, usually we put 0 here. Usually, when it comes to moles at start of the product, we put 0. In this case, we can't, because the question tells us that already there is an initial amount, already there's X amount of nitrogen tetraoxide. It's not 0, it's there, if you read the question properly. So it says the 2 moles of nitrogen dioxide and an unknown amount of nitrogen tetraoxide. I'll call this unknown amount X. In fact, the question, which is worth 9 marks, is asking us about this unknown amount. We go further. Let's work it out together and see how far we can go. It goes on to say at equilibrium, it was found that nitrogen tetraoxide, its concentrate, nitrogen dioxide, sorry, its concentration is 0.4 moles per decimeter cubed. So I'm going to come here. At equilibrium, I've got 0.4 of this guy. Now I can fill up the table. Let's begin together as a family. Let's start here. Obviously, I've got the concentration of nitrogen oxide at equilibrium. Concentration by formula is equal to N over V. That's what concentration is. Now, if I have the concentration of nitrogen dioxide, 0.4, the number of moles of nitrogen dioxide, I don't know. I'll call that N. And then the volume in this case is 2. You were given that the volume is 2 decimeter cubed. Math suggests that N, the number of moles of nitrogen dioxide, is 0.8 after cross multiplying here. So I'll put here as 0.8. That's very important for you to understand. All right, so that's important. Let's get that clear up. All right, let me continue with this one. Remember, we are looking for X, and X is the number of moles initially of the product nitrogen tetraoxide. Now, if we continue with the table, at start, you had 2 of nitrogen dioxide. At equilibrium, you've got 0.8. So you had 2 in the beginning, and then now you got 0.8, which means that you used, remember the step number 3 right here is used or produced. And in nitrogen dioxide, I'm using it, while this guy here, I'm producing him. So then if I had 2 in the beginning, then suddenly I've got 0.8. It means I used 1.2 right there. That's an important thing. I used 1.2. But then I need to continue, and I need you to remember right here, at this stage right here, at this step, please use ratios. I usually call it step number 3, as step number 1, 2, 3. At step number 3, please use ratios. Step number 3, please use ratios. So I'm going to compare nitrogen dioxide to nitrogen tetraoxide, stage number 3. The ratio is 2:1. And then I notice that I've got the moles. I have the moles of nitrogen dioxide, which is 1.2, and those of nitrogen tetraoxide, it's X. If I do the cross multiply part here, cross multiply, then it becomes 2X, which becomes a 1.2, then X becomes equal to 0.6. So here I'll put 0,6. That's why I used ratios in step number 3, so that I can get the number of moles of nitrogen tetraoxide that was produced. Please remember, nitrogen tetraoxide, you're producing it. You are not using it. This is why now, in this particular part here, right here, this is why now, this is what I'll do. You see, I had X in the beginning of nitrogen tetraoxide. I produced 0,6. So at equilibrium, I must have X plus 0,6. So I must get something clear here. When it comes to the reactants, the guy that I used, I subtract. What do I mean? 2 minus 1,2, 0,8. When it comes to the products, what do? I add X plus 0,6, X plus 0,6. So these are the moles at equilibrium of the nitrogen tetraoxide. But I'm looking for X. I need to continue. Check this out. You see, at concentration, let's go back, people. Concentration is number of moles over volume. The number of moles of N2O4 is X plus 0,6, all this divided by 2. Remember, the volume is 2. That's what you have. So then how do I get X? How do I calculate X? You're given Kc. Kc you were given is 2. That's what Kc is. It's 2. So let me just enlarge my board here and make sure that this thing is clear. All right, let me do this so that at least everything is pretty much fine. Okay, right. Just gonna put that there. Okay, people, let's go. Wanna work. Now, I was saying to you guys, Kc. You need to write the expression and you get a mark for writing the Kc expression. Kc expression is concentration of product, which is N2O4, right, over concentration of reactant, which in this case is NO2, and this time is to the power 2. You are given that Kc is 2, all right? So Kc is 2 from the question, and you're looking for X. Now, the concentration of N2O4 is this guy. There you are. That's the concentration of N2O4. It's this one here. Now, I advise that you don't put it like that. You don't put it as X plus 0,6 over 2. Don't put it there. I advise that you don't do that. Wow. Just keep it as N2O4. I'll show you why, right? N2O4. Then I know the concentration of ENO2. In this case, it's 0,4, like that. Okay? Just keep it like that. Cross multiply. At the end of the day, this is what I'm going to be having. Follow my lead right there. I'm going to be having 2 times 0,4, which is 0,8, is equal to the concentration of N2O4, like that. But notice again, N2O4, this guy, N2O4 is concentration, is the one written X plus 0,6, all this divided by 2. That's what it is. So this 0,8 is equal to, I don't have a calculator, guys, so help me out to get this right. Help me out to get this right. So I'm going to cross multiply here, 0,8 multiplied by 2, and I think it's going to be 1,6 is equal to X plus 0,6. Vicky, you got your hand up. I want to attend to you right now. I'm going to unmute you. Go ahead.
Say.
Yeah.
It's on your 0,4. Aren't you supposed to square it?
Oh, yes, it's the squared one. Okay, I see what you're talking about there. It's because I don't have a calculator with me here. Let me mute that. Okay. All right. What I want you guys to do, thank you, Vicky, for that. I'm going to square that. Then this is also going to be, I'm going to take that out quickly. Thank you for that reminder. This is not going to be 0,8. Definitely not 0,8. There you are. Okay, help me out. What answer did you get? Please write it on the chat group so I can just copy it. I don't have a calculator. 2 times 0,4 squared. Put it on the chat so I can see what's going on. There we are. 0,32. Thank you. Someone just posted 0,32. So 0,32. Right. Again, it's going to be equal to X plus, thank you so much, guys. X plus 0,6. All this divided by 2. That's 0,32. Cross multiply. 0,64 is equal to X plus 0,6. Maths will tell me X is equal to 0,04. I think I'm right. If not, correct me. That becomes the answer right there. What's 0,64 minus 0,6? I think it's 0,04. Am I right or am I right? talk to me. Give me a yes on the chat so that at least we can work together. I don't have a calculator. I don't know where it is in this house. All right. Okay. Beautiful. There you are. You're right. Thank you. X is equal to 0.04. Guys, listen, it's not a mistake that sometimes the moles of the product at start cannot be 0. I know it's usually 0. If they tell you that there's an unknown amount, please don't assume it's 0. Just put that X. In this case, definitely X would make sense. Please, guys, write this down quickly. I'm going to give you about a minute and a half or a minute or less to write this down quickly. Those that are coming in through, then I'm going to send this handout now. There are people that don't have it. I'm going to send the handout. Now, I sent a handout on WhatsApp. That's the one I'm going to go to after this question. This question is on the small book on Star Schools, page 143, 2010 March. But some people don't have the small book on Star Schools because they're not from Star Schools. That's fine with me. I will make sure that I give it to you as soon as is possible. All right, let's go. I'm on the next one. Quickly write this down, guys. Let's go. I'm on the next one. Write this one down. All right. Thank you so much for that. Guys, 30 seconds. I'm going to take this out. I prefer that you write. I prefer that you write because when you're writing stuff, that's how you know stuff. If you don't write, you'll never know. As you write, you know stuff. I want to go on to my next one, which is 8.52 and then 8.53 as well. Then I'll take it up from there. 8.52 and then 8.53 as well. Very important. 10 seconds, I'm taking this one out. 10 seconds, I'm taking this one out. Make sure that you write as quickly as is possible so that you can see what's going on here. All right, let me do this as well. Okay, put it as PDF. Okay, right, I've saved this thing on my laptop. I'll be able to send it to you later on. Okay, just in case someone has not finished this, I'll be able to send it to you later on. Let me just now go to my next question. I'm ready for my next question. Here we go. It says the plunger is pushed into the container, causing the pressure of the enclosed gas to increase by decreasing the volume. I've got to write this down. There's an increase in pressure now. From what you're looking at the equation is 2 and then 1. So in terms of the moles, 2 and then 1. That's what you're looking at. So they're telling us that now the plunger is now pushed into the container and causing the pressure of the enclosed gas to increase. There's an increase in the pressure. Question, how will this change affect the amount of nitrogen dioxide at equilibrium? Only write increase, decrease, or remain the same. Notice that your formula is like this. Your equation is like this. And then you've got N2O4. The question is, when you've increased the pressure, Lee Chatelier must speak to us right now. When you've increased the pressure here, how will this affect the amount of nitrogen dioxide? Let's do Lee Chatelier. An increase in pressure, that's the disturbance that happened. The system must favor a reaction which decreases pressure. To decrease pressure means to move from big number to small number. So let me go back again. The disturbance here is that there was an increase in pressure. What should happen? There must be a decrease in pressure. What is that? According to Lee Chatelier, there must be a decrease in pressure, which is to move from big number 2 to small number 1. In other words, I'm favoring the forward reaction. What happens to the amount of nitrogen dioxide when I'm favoring the forward reaction? If I favor the forward reaction from greater number of moles of gas to lesser number of moles of gas, from 2 to 1, if I favor the forward reaction, the amount of nitrogen dioxide, this guy, decreases. The question was, write increase, decrease, or remain the same. And my answer for all of this is that in the case of nitrogen dioxide, in a case where there was an increase in pressure, which must be followed by the system decreasing pressure, to decrease means to move from big number 2 to small number 1, forward reaction is favored. When forward reaction is favored, the amount of N2O4 decreases. So the answer is decreases. Then the next one is explaining it. 8.53 is explaining it. 8.52 decreases. Right, I want to explain by detecting. So listen to me. You got to write what I'm going to say right now. Okay? You got to write what I'm going to say. So 8.52, it decreases. Amount of NO2, amount of nitrogen dioxide decreases. 8.53, I'm reading the question. Check it out. Use Le Chatelier's principle to explain your answer to question 8.5.2. All right, fine with me. Here's my explanation. An increase in temperature, write the following. An increase in temperature will favor the reaction. An increase in temperature will favor the reaction with less number of moles. An increase in, why am I saying temperature? An increase in pressure, right, will favor the reaction with less number of moles. Write it down. An increase in pressure will favor the reaction with less number of moles. That is from 2 to 1. An increase in pressure will favor the reaction with less number of moles. That is from 2 to 1. Full stop. This means the forward reaction is favored. 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 Therefore, the amount of NO2 decreases. Therefore, the amount of NO2 decreases. Therefore, the amount of NO2 decreases. Okay, let's go to the handout on WhatsApp now. Go to the handout on WhatsApp. Go to the handout on WhatsApp quickly. We're going to be doing question on page 1, the very first question on page 1. That's why one that we're doing. The handout on WhatsApp, guys, people, please quickly, right? Handout on WhatsApp. I sent it. I want to share the whiteboard screen where I'm going to be doing the questions now. That's what I want to share. Okay, let's begin on that question together. All right, let's start the handout on WhatsApp. Very first page is 2015 Senior Certificate. Please mark that, 2015 Senior Certificate. That's the question that we're going to do right now. All right, I want to start reading. Let's start. Page 1, that's on the handout that I sent on WhatsApp. Please, please, please try to look for it. Try to make sure that you get it right. Handout on WhatsApp. Okay, here we go. Initially, right, NH4HS solid is initially excess NH4HS solid. This is ammonium hydrogen sulfide, right? Ammonium hydrogen sulfide. Okay, somebody raise their hand up. I want to attend to that quickly so that I can take it up from there. Right, so I'm saying your hand is up.
Say, I can't access the document that you send on WhatsApp.
Try to download it again. Try to re-download, please, because I sent it just now on WhatsApp. Try to re-download. Anyone who can't access it, try to re-download on that one, please, by all means. Okay, those that cannot hear me, someone just sent a message. Okay, can somebody on WhatsApp, right, on one of the Mr. X classes group, please tell that person to go to the left-hand side of their device and press dial over internet or join in audio, whichever case it is. Please, by all means, tell them that. Right, so I'm saying, look for that one. You should be able to get it. I'm going further. Right, initially excess ammonium hydrogen sulfide is placed in a 5 decimeter cubed container. The container is sealed and the reaction is allowed to reach equilibrium according to the following balanced equation. Notice that this is a heterogeneous equilibrium. You've got a solid and you've got gases. So it's not homogeneous, it's heterogeneous. You've got solids and you also have gases, as can be seen right there. Now, I'm reading State Le Chatelier's principle. Can I skip that one because people are familiar with that? So again, guys, please make sure that you know Le Chatelier by head. In the exam, your definitions are 2 marks or 0. 6.2. What effect will each of the following changes have on the amount of ammonia at equilibrium? Right? Only increase, decrease, or remain the same. Increase, decrease, or remain the same. Now listen to this one here. What effect will each of the following have on the amount of ammonia at equilibrium? Right? Only decrease, increase, or remain the same. If more NH4HS solid is added. All right, let me explain. Now, I want you to understand something pretty significant here. When it comes to you're adding a solid at equilibrium. Now, Kc is about gases. And if you go back to your notes, you will notice that there's something that I put across when I was talking about Kc. Remember that this is at equilibrium. There's something that I put across when I was talking about Kc, where I said at the end of the day, when you've got a Kc, you don't include the solids. And then the mass of the concentration of the solids or the effect of the solids is a constant. Or I actually put it in your notes and I said it's 1. So in this particular case, when you add more ammonium hydrogen sulfate, what will happen to the amount of NH3 ammonia in that case? Nothing. It remains the same. The reason is because you are adding a solid, and around equilibrium, the concentration of a solid is irrelevant. This is why you don't even use it when it comes to you calculating Kc. So because this is at equilibrium, then the ammonium, the NH4HS added will not have any effect on the amount of ammonia. So it will remain the same, right? That's what will happen right there. It will remain the same. So 6.21 remains the same. iPhone, ask me, let me help you. I want to unmute you now. Go ahead.
Because you said if it's at equilibrium, you can't do anything when it's a solid. So what if it was not at equilibrium? What would happen?
Then it will affect it. Then that's when you start applying Chatelier. That whole thing of, okay, I've increased the concentration of NH4HS. That means that I must look for a reaction which decreases it. To decrease it means to move forward. Forward means I'm making more ammonia. So that will happen if it's not at equilibrium, right?
Okay.
Beautiful. 6.22. Let's talk about concentration right now. 6.22. Let's talk about concentration. No, temperature. It's actually temperature. Zanele, you got your hand up. I'm going to unmute you. Go ahead.
So, is it the same? Is it the same with liquid?
Yes, it's the same with liquid, but it's not the same with aqueous. It's not the same with gas. All right? Gas and aqueous, those are two different things. They are involved in Kc. So I want you guys to remember that, please, by all means. I don't think in class or even the other guys that I teach elsewhere, don't remember, I didn't mention this, but I want you guys to always remember that in this particular case, you're going to have nothing happening, remains the same because you added a solid at equilibrium. A solid is not involved in Kc. It doesn't change anyone's concentration at equilibrium. Let's go. Temperature has increased. Temperature, remember, affects Kc. Temperature affects Kc. Now, I'm looking at the equation now. Follow my lead. I'm looking at the equation. So if you look at the equation, delta H is greater than 0. Delta H is greater than 0. That means that the forward reaction is endothermic. So what have I done to temperature? In this case, I have increased temperature. So the increase in temperature. Please always remember, an increase in temperature always favors the endothermic reaction. When you increase temperature, you favor endothermic. That's a statement that must always be remembered. Increase in temperature favors endothermic. Then I come here to my equation. Who is endothermic? Is the forward reaction. So if I'm favoring the forward reaction, what's happened to the amount of NH3? Look at this. When I'm favoring the forward reaction, I'm making a lot of NH3 because I'm favoring this reaction, forward reaction, where NH3 is being made. So in this case, NH3 amount will increase. So for 6.2.2, it increases. Definitely, it will increase. And I want you to remember that in this particular case. So an increase in temperature favors endo, whose endo is the forward How do I know endo is forward? Delta H is greater than 0. And then what's happening if I'm favoring forward? I'm making more NH3. And that becomes your answer. Remember, temperature affects Kc. Temperature affects equilibrium position as well. So in that case, it increases. Right. Luckily, they didn't ask us to be able to explain all of this, but here's a crazy question with 6 marks. Here we go. The equilibrium constant for this reaction at 218 degrees Celsius is 1,2 by 10 to the power negative 4. My people, remember that Kc is always given at a specific temperature. So Kc is always temperature dependent. This is why in every question, they will tell you that the Kc8 at a certain temperature, because whenever you change Kc, you change temperature. So don't forget that. Sharp. Let me work. Let's work together and see how far we can go. The question says Kc is that. Calculate the minimum mass of ammonium hydrogen sulfide that must be sealed in the container to obtain equilibrium. Very interesting. 6 marks on that one. All right, let's work together as a family. I'm just going to draw my stuff here. So I'm going to start off with my molar ratio. Then I'm going to have moles at start. Okay, moles at start. Then I'm going to have moles used or produced. And I'm going to have here moles at equilibrium. Okay, let me get this done. And then I'm going to have here concentration at equilibrium. All right, let me show you how this question works. Follow my lead. In this question, notice that you're only given one value, Kc. You're not given anything else. You're just given Kc. All right, and I want you to understand what's going on here. Follow my lead as a team. Okay, let's do this together. All right, I want to make sure that everything is cleared up. Also be drawing this while I draw this so that at least it becomes easier for you. Okay, there we go, and there we go. 3 things are involved, and somebody's saying, but say you said the solid is not involved. Yeah, it's not, but in the beginning it's there, and it's part of what I need. So the solid is NaN4, is NH4, and then that's HS. All right, there we are. Then the other one is ammonia, which is NH3, and then the other one is H2S. Luckily for you, if you look at the molar ratio, it's 1:1:1. That's the luckiest thing we have. 1:1:1. That's a very important thing. Now, moles at start. For NH4, let me just explain. We're going to use this guy. He is my reactant. We're going to be producing this guy, PP. There at the top, I'm going to produce them, then I'm going to use. In the beginning, you can only use what you have. So moles at start of NH4 is X. There. I don't know it. I just don't. Then for ammonia, it's going to be 0. I don't have it. This is unlike the previous question where they said initially there was an unknown amount. This time they didn't say that. So it's okay to say it's 0. All right. So in the beginning, I don't know how much of X I have. I just don't know. All right. Let's keep going further. Now, because you're having 1:1:1, let me just help you understand this further. Moles used or produced. According to the molar ratio here, 1:1:1. Let's say here the moles that I produced of ammonia are X. Let's say they're X, right? Let's say they're X. That means the moles of H2S4, H2S also must be X because the ratio is 1:1. And it's 1:1. That's the ratio, right? I want to show how I'm going to get the X at the end of the day. I'm going to come down to this part. I'm going to come down to this part here, and I'm going to call this X over 5, or rather X rather than X over 5. Let me just take the X over 5 over the next one because that's the concentration right there. Okay, let me work it out. Follow my lead. Now, because I'm producing this, I'm going to add 0 plus X becomes X, and I'm producing this 0 plus X also becomes X like that. Now, the concentration at equilibrium becomes X over 5. How do I know? Concentration is number of moles over volume. So the number of moles of ammonia is X, volume is 5. I'm given that in the question. Yes, volume is 5. Even here, it's going to be x over 5. Follow my line of thought. I want to show how you break it down like that. Now, Kc, remember the only thing that you have is Kc. That's the only thing. You don't have any other values like moles at equilibrium of what, or concentration at equilibrium of what. In this case, here, I'll put a stroke. Because at this particular position, right there, here, I don't deal with the concentration of the solid. I don't deal with it at all. Even at equilibrium, I don't deal with it at all. But at start, I had it. Because without this solid, we would never have this ammonia, which is a gas, and this hydrogen sulfide, which is also a gas. We wouldn't have it. So in this case, therefore, Kc, you are given as a value, right? But before a value, I want to write it as an expression. They are gases. Kc is about gases like this. Right, that's what Kc is. It's about gases. Now, Kc is 1,2, and I need to move quickly because I don't have a calculator here, so I know what I'm going to do without the calculator. Trying to write this properly. Kc is 1,2 by 10 to the power, I think it's -4, all right? -4. All this is equal to the concentration of ammonia. At equilibrium, it's x over 5, all right? There you are. Even that other guy is going to be x over 5. There you are. The rest is math. Math says x squared over 25, all right? That's 1,2 by 10 to the power -4. All right, follow my lead, and I'll show you why it will make sense now when you start doing this. At the end of the day, my x, if I do my math after square rooting, because I'm going to cross multiply by 25, then I'm going to square root. You tell me, cross multiply by 25, then square root. X at the end of the day, I have my answer here, becomes 0,0547 moles. All right, let's stop there and let me teach you. Right, follow my lead. Let's stop there and let me teach you. Listen to this. Now, at equilibrium, x is 0,054, but x is here, is this guy. Is the moles of ammonia at equilibrium is the same as the moles of H2SO4 at equilibrium. And then we are looking for the mass of this guy. And again, I put it as X. And someone says, but say, how are they the same? They are. 1 mole of ammonia and 1 mole of H2SO4 is produced by 1 mole of NH4 SHS. This is why at the end of the day, these guys that are produced from a ratio of 1:1 from NH4HS. So the moles of ammonia produced at equilibrium, moles of H2S produced at equilibrium are the same as the moles of NH4HS that was at start. Because the ratio is 1:1:1. Even if I was to put it here, still it will make sense at the end of the day. And that's why if I put it here, let me say this, right? Let's say this, remember I said in the beginning, this was X, the number of moles of ammonia. And then this one will be X also by 1:1. This one also will be X by 1:1. Then in this case, notice that I add, then here I subtract. That's why I have nothing here. I have nothing there. So therefore, X here, this X here is the moles produced. And these are the moles, all of them that we had at start, we used them. That's why right there towards the end, we have nothing. Therefore, no effect at equilibrium to your value for Kc. So this is X as it can be seen. All right, I'll go back to this. Now, since I have X is moles. I mean, I'm not looking for moles. I'm looking for mass. Mass of who? Mass of NH4HS. That's what I'm looking for. I have its moles now at start. I would like to know its mass. That's what I would like to know. It becomes easier now when you think about it. Once you got the moles and you're looking for the mass, it becomes a bit easier to think about it. Follow my lead. There's a formula that we know by head, and I just want to write this down quickly on this particular formula. It says number of moles is equal to mass over molar mass. Periodic table must come into life. The mass there will be number of moles times molar mass. So I'm looking for the mass of NH4HS. Number of moles, 0,0547 multiplied by the molar mass of that guy, and I think it's 51, okay? If you use your periodic table, at the end of the day, the mass becomes 2,79 grams. I want to move quickly because I don't want you guys to calculate because of our time. We need to utilize this as much as possible, learn as fast and as much as possible. That becomes your answer. 2,79 grams of NH4HS was what we had in the beginning. We had gotten its moles. How so? By comparing and saying, oh, okay, imagine the X is the moles of NH3, 1:1, 1:1, and then I'm going to use all of this. That's why I have nothing here, nothing here. I'm not going to be having this at equilibrium. I don't use it, not just because I've used all of it, but also as well because at the end of the day, that becomes irrelevant because it's a solid. That becomes the answer for that question. Write that one down. Now, the question that I'm picking today are not your usual ones, not your usual way of getting your KCs and stuff like that. And I want to make sure that everyone is clear on that. Let's go. I want to go to 6.4 quickly. Can you hear? Go ahead.
Sir,
Yeah.
I seem to have missed something on the table. How did we come about? How did we get 1 over X?
1 over X.
Yeah.
Waiting, Neville. 1
over X.
I got X over 5.
No, I mean at the initial.
Or this one, 1 over, you mean this one 1, and then there's an X underneath there.
Yes.
Okay, let me just erase and see what you're talking about here. All right. Are you talking about this 1 over X part here?
No, the one on the second column.
Second column, right?
Yeah.
This one.
Yeah.
I remember I said to you, okay, this question is a trick one. I'm saying I'm coming to you. This question is a trick one because you don't know the number of moles of ammonia that was produced. So you call it X. And why this X is X everywhere is because the ratio is 1:1. So this is stage number 3, where you use ratios. Mute yourself, Neville, then I'll be able to help you out understand this. This is X in the beginning. So this is X that was produced. And then I'm saying, according to the ratio 1:1, this will also be X. Imagine if it was a number. If it was a number, this will be 2. This will also be 2. That will also be 2. X, 1:1:1. That's what I'm saying. So at the end of the day, I just put that as X to say to us, okay, these are the moles that were used, that were produced at equilibrium, or that were produced by the fact that I was using something to produce. So at the end of the day, you're going to have a situation. Let me just write this as X there. Yeah. At the end of the day, this is X for the ammonia that was produced. In its ratio, it's also X. X is just an unknown number. The problem with this question is I was only given this information, KC, only. Nothing else but KC. So because I'm just given KC, I'm using the X's as unknowns. And luckily for me, it's 1:1:1. So everything else becomes clear if I look at that from that perspective. That's a good one. I'm hoping you understand as we're going along. Right, I just want to give to the next person. Neville, you let me know if you don't understand. I want to give to somebody else quickly before I go to my next question. Right there. There were 2 more people that had raised their hands. I want to deal with you. Let me start off with, let me see, who's that? Tracy, then I'll go to Ntabiseng.
Sir, can you hear me?
Yes, I can.
Okay. The last calculations where you were calculating mass, I want to know how you got the 51 using the information from the periodic table.
Okay, beautiful. Thank you for that question. Let me explain to you right now. So you can mute yourself. Thank you for that one, Tracy. Let me explain. Guys, eyes on this. Okay, so I just took it from the memo because I don't want us to work, but this is how they do it. NH4, forgive me for that one, and then HS. All right. Okay, so nitrogen should be 14. plus hydrogen lana, you've got 4 hydrogens, right? H4, and hydrogen is 1. So it's going to be 4 times 1. I'm adding, plus another hydrogen, which is 1. Sulfur is 32. All this must give you 51. Just confirm that. All this must give you 51. So guys, remember it's 14 for nitrogen, plus how many hydrogens do I have? I have 4 of them. Each hydrogen gives me 1 in the molar mass on the periodic table, plus that other hydrogen there, that's 1. Then sulfur is 32. Confirm, I think that should give you 51. So that's how you get it right. As you can see, Tracy right there. Okay, I want to give over to the next person. Type saying you got your hand up. I just want to make sure that I sort you out quickly and you can be able to ask me a question. Guys, please write this one down, and then I'm going to move on to my next one. So you add, Tracy, you add like right there. Okay, I'm gonna move on to my next one quickly. Okay, sharp. Type saying your hand is up. Let me just help you out. Guys, people keep being knocked out by network here, so I keep admitting people. It's okay, we'll learn as we go on along. Okay, type saying, unmuted. You are unmuted.
Can you hear me, sir?
Yes, I can.
I wanted to clarify including that one that has a solid to say. I wanted to ask Uti, if maybe let's say I didn't include it, like the whole table, does it ihamba KC or normal, like it's just that you calculating KC. Let's say maybe like there's a solid gas and a gas, right?
Mm-hmm.
And then that's maybe calculate KC like a normal way. As I'm back near to KC. Both are involve a footy, or like you were just going to include the gas. Let's say gas pair.
We only include the gases. So I'm saying we only include the gases right there. So where you were going to use it was, let's say you were given a number here, right? Given a number, you're probably going to use that number right there or put that number there. But otherwise, when it comes to KC, guys, KC is all about gases. This is why even in the KC expression here, there was no inclusion of solids or liquids. We don't include them. So you don't put it there. You only deal with it in terms of gases. All right, that's fine. All along, it's gases, as can be seen. Okay, there was a question, I think, Utobile, or I didn't read the name properly. You're asking about a periodic table and that they've got different values. Okay, I understand. I think on Turbo or the book that you have, you've got different values. But on the final exam, you'll have a periodic table that you're going to use, right? You use that particular periodic table in the exam. That's the one that you have. It's going to be having those straight values. The one on Turbo, it's got, if you're using Turbo or any other book, sometimes those ones have got decimals. The one on the final exam is rounded off. Okay, so the one for the final, and here I'm using the one for the final exam where everything's rounded off. Okay, next question. Thank you so much for that one. I'm moving and go to the next one. The pressure in the container is now increased by decreasing the volume of the container at constant temperature. This is interesting. How will this change affect the number of moles of H2S produced? Okay, let's get down to something here. Now, tell me something. Look at this. On the right-hand side, we've got 2 moles. 1 mole of ammonia and then 1 mole of H2S. Then on the left-hand side, there's no gas. There's nothing like that. There's no gas. There's a solid. So let's put it 0. On the left-hand side, there's no gas. There's a solid. Let's put it 0. The question says now, the pressure in the container is increased. Chatelier comes into life. We increase the pressure. What should happen? There must be a decrease in pressure. What does a decrease in pressure do? It's moving from the particular big number 2 to small number 0. And I want you to remember that. So in this question, which is not something that you probably knew, in this question, if on the left-hand side, there's just solids. So it means in terms of gases, on the left-hand side, the moles are 0. Then on the right-hand side, there were 2 moles. So what have I done? The system tells me that, I've disturbed by increasing pressure. the system must disturbed by increasing pressure, the system must decrease pressure. To decrease means to move from big number 2 to small number 0. So I'm favoring the backward reaction. And because I'm favoring the backward reaction, question was, what happens to the amount of H2SO4? Notice, guys, when I'm going backwards, I'm using H2SO4, no, H2S, sorry. What happens to H2S? I'm using H2S. As long as I'm going backward, I'm using H2S. So the amount of H2S, the answer is it decreases. And we need to explain that nicely. This 0 part is very important, just in case you didn't understand it. It's super important that you understand as to why we have a scenario like that. So in this case, you had nothing, 0, 2, then you increased pressure. And remember, you only increase pressure by decreasing volume. So then because you have increased pressure, the system must decrease pressure. To decrease means to move from big number 2 to small number 0. We're favoring backward. What does backward do to the amount of H2S? It decreases it. And so the question says, how will this change affect the number of moles of H2S produced? It will decrease them. Fully explain the answer. We're going to be using Chatelier. Write the following. I'm now detecting. Write the following. It decreases. Decreases. Then we say, when the pressure is increased, the reaction with the smaller, when the pressure is increased, the reaction with the smaller amount of moles of gas, the reaction with the smaller amount of moles of gas, smaller amount of moles of gas is favored. Smaller amount of moles of gas is favored. That is the backward reaction. That is the backward reaction. That is the backward reaction. Okay, that is the backward reaction, as can be seen. So I'm pretty clear. And once it's the backward reaction, the amount of H2S decreases. Page 2, guys. Let's go to page 2. That's my next question, my last one. Then I'm going to give you something to try on your own now. Let's go. Page 2, 2017 Eastern Cape. Page 2, 2017 Eastern Cape. No. Can you go to page 8? Hey, let's change things here. Page 8. I'm sorry, guys. I'm sorry. Page 8, 2014 November. Page 8, 2014 November. Page 8, 2014 November. Let's go to that one, okay? Quickly. Page 8, 2014 November. I'm reading in your hearing. Let's all go there. It's the handout that you have on the Star Schools, on the chat group that you have, the WhatsApp group, the one that I sent. Please, let's all clearly go there. Listen to the question. A certain amount of nitrogen dioxide gas is sealed in a gas syringe at 25 degrees Celsius. When equilibrium is reached, the volume occupied by the reaction mixture in the gas is 80 cubic centimeters. So let me be clear on something. Volume is 80 cubic centimeters. The balanced chemical equation for the reaction taking place is what you see there. So you've got dark brown and you've got colorless. Those are the colors of the substances. In other words, if I was to interpret this, I'll say the nitrogen dioxide is dark brown. So your reactant is dark brown and your product is colorless. Delta H is less than 0. Forward reaction is exothermic. 6.1, we skip it. We know it. To define chemical equilibrium, we now know. 8 marks, that's what I want. 6.2. At equilibrium, the concentration of the nitrogen dioxide is 0.2 moles per decimeter cubed. Okay? The equilibrium constant for the reaction is 171 at 25 degrees. Calculate, 8 marks, the initial number of moles of nitrogen dioxide placed in the gas syringe 8 marks. So calculate the initial number of moles of nitrogen dioxide placed in the gas syringe, 8 marks. This reaction is pretty popular, so let's work it out together. I need my table first, as usual. So I'm going to have my molar ratio. You better be writing. Then I'm going to have moles at start, okay. Then I'm going to have moles used or produced. I'm going to use shortcut now. I'm saying moles at equilibrium. Then I'm going to have concentration at equilibrium. Right, we use the information that we have. Everybody is a gas right there, so everyone is involved in Kc, and you're given the value for Kc, which is a great thing altogether. So we're going to use all of this. Write it down as I write my own down here so that we can understand. Take this lesson very seriously so that it can help you out, because we are not going to do this again. This can save your soul. All right, so I'm going to have this as NO2, okay? Then the other one is N2O4. Okay, we start. Molar ratio is 2 and is 1. I want to fill up my information that I was given. Moles at start of NO2, I don't know. X, that's what they want me to find out anyway. Question says, calculate the initial number of moles of NO2 placed in the gas syringe. Then here, for N2O4, it's going to be equal to 0 right there in the beginning. Later on, I was told that, Yazin, when it came to concentration, the concentration of NO2 is 0.2 moles per decimeter cubed. So I got to write this down here. All right. So this one is now 0.2 moles per decimeter cubed. Right. Now I can fill up the table. I'm given Kc. I am given Kc. And I'll just want to write this down. So UKC is concentration of nitrogen tetraoxide over concentration of nitrogen dioxide, but it's squared. And then Kc is 171. Concentration of nitrogen tetraoxide at equilibrium, I am pretty clueless on this. Then concentration of nitrogen dioxide at equilibrium is 0.2 and it is squared. I need help. I need help. Can people help me out on this particular question right there so that at least I can understand what is going on? Help me out so I can see what's going on. Help me. Right? Help me. How do I get this concentration of N2O4? What do I get this concentration of N2O4? Write it down for me on the chat so at least I can get it right. Right? Mina, okay, I think, is it 6,8,4, right? Thank you so much. 6,84 moles per decimeter cubed. So I'm going to have this guy as 6,84 moles per decimeter cubed. All right, I'm working backwards. Thank you so much, guys. I really appreciate what you're doing right now. Great. So I'm going to have this as 6,84 moles per decimeter cubed. So this becomes the concentration of N2O4 at equilibrium. All right, N2O4 at equilibrium. We're working backwards. We'll just work backwards. Follow my lead. Right. So I'm saying to you now 6,84. Now, this is moles at equilibrium. Moles at equilibrium. I'm now here, moles at equilibrium. We know the formula. Okay, somebody just wrote here. We know the formula that says number of moles is equal to mass over molar mass. So I'm looking for the moles at equilibrium, mass over molar mass. Okay, help me. All right, number of moles. Oh, we don't even need to do that because we've got the concentration. Yeah, we don't need to do that. And we've got the volume. I can help you out. Okay, let me just do this. Let me take this out. An easier method because I got the volume and concentration. So since this is concentration, concentration is equal to number of moles over volume. That means that the number of moles become concentration times volume. Let me just take out this red line here. Thank you. Okay. Follow this. Just want to write it nicely. So concentration is number of moles. Number of moles is concentration times volume. So let me start off with this guy. I want the moles of him. His concentration is 6,84. And what is his volume? Volume is 80 cubic centimeters. You were given. So it's 80 divided by 1,000. Okay? 80 divided by 1,000. Guys, help me out. I really don't have a calculator here. Help me out. What'd you get? 80 divided by 1,000? Okay, I'm just trying to look for 6,84 times 80 divided 0,5572. Okay, somebody just put that across. Okay, I'm gonna write it down as 0,5. Let me read it properly. This 0, hold on. 0,5472. All right, that's right. 0,5472. Okay, let me minimize everything. Moles. So these are the moles right there. So I've got 0,5472. Now I can also get the moles of this guy here because I have his concentration as well. And so I can get the moles of him. I can, because I also have his concentration. I can get his moles. So number of moles of NO2 will be concentration of NO2 0,2 multiplied by volume, which is 80 again, divided by 1,000, like this. Talk to me. What you get? Let me know how you get this one. These ones are the number of moles of N2O4. Okay, we just want to make sure that is clear up. N2O4. What do you get? I'm just looking for the answer now. Help me out. Okay, I'm looking for my people. Let me use it from my phone here to become easier. Okay, 0,016. Thank you. So I'm going to have it as 0,016. So I'm going to have it as 0,016 right there. All right. So look at this. Let me help you. In the beginning, guys, you had 0 of this guy. Let's keep going. You had 0 of this guy. And you made 0,574 moles of him. There. 0,5472. Let me write that properly. 0,5472. That's how much you made of him. You produced. Now, look at the ratio here. It's 2:1. Remember, I'm looking for X. That's what I'm looking for. The ratio is 2:1. So if I come here and say, okay, so in the beginning, the ratio of NO2 to N2O4 is 2:1 right here. Then I say to myself, whose moles do I know that I produced? This guy, which is 0,5472. Then I'll call this X and I cross multiply X 2 times that. Please give me an answer for that one. 2 times 0,5472. I'm waiting for you guys on the chat. Just somebody to send it to me. Okay, I'm looking at the chat. Nobody has sent yet. Okay. 0,5, 1,0944. Thank you. I'm gonna have this as 1,0944. There. Okay, type of thing. You raised up your hand. Let me just finish up this question quickly so that at least we can set it up nicely. Okay. Okay, let me just attend to you just in case I didn't. Yebo, type of thing. I've unmuted you. I've unmuted you. Type of saying. Okay, I'm not winning here. All right. Okay, Snenhlanhla, maybe you can try that. Go ahead. Snenhlanhla.
So can you hear me?
Yeah.
So please can you go to one of the groups? Kona please send a message with you, please. She wants to ask a question, but I don't know how to pronounce her name.
She wants to ask a question.
Yes, she's been saying that.
Okay. Okay, you just raise up your hand using the platform. Okay, I'll attend to it now. I'm gonna attend to it now. I see I'm not on the group here. I'm definitely not on the group right now. Okay, right, I'm gonna attend to that. Sandiswa, you have your hand up. Yes, Sandiswa, go ahead. I have unmuted you. Sandiswa?
Hello, sir.
Yes. Ask me. Go ahead. Ask a question.
Hello.
Yes, we can hear you.
So is it wrong if I round off my mode and then I calculated the change? It's 1,1. So is it wrong if I'm like under off my mode before putting it out?
Okay, is it wrong if you round off before putting blah blah blah, right? No, not really. No. It's not wrong, but I advise against it. I prefer that you round off towards the end. That's what I prefer. So I really advise against it, but though it's still pretty much okay, right? But I really advise against it.
Okay.
When I will check for you guys the exam guidelines for this year, what they are strict on or what they don't mind, and then I'll get back to you. Thank you for that beautiful question, Sandiswa. Appreciate. All right, guys, let me continue with this question and finish it up. Taviseng, I'm going to come back to you because I can't hear you. All right, beautiful. So mute yourself, Sandiswa, sorry. Then listen, guys, I'm looking for X. Hold on, I'm looking for X. That's what I'm looking for. Mathematically speaking, remember that this NO2 is your reactant, so I'm using it. So in math, I'll say X minus 1,0944 will be equal to 0,016. That's what it is equal to. This is what I put across here. I've already written it right there. And then please, guys, tell me what my X is at the end of the day when I'm doing my math. Remember that it is your reactant, so you're using it. What is X equal to? Thank you so much. 1,11 moles. If you look at your memo, there are 5 ways of doing this. And the one that I've done is not even there. No, it's there on the memo right there. And this one for me becomes easier for all of you to understand. The other ones can look a bit complicated, but this one is pretty much straightforward. So that becomes the number of moles of X in the beginning. Write that one down. Then I'll move on to another thing. 6.3, we're going. After this, I'm going to give you a question. Just go. 6.3 to 6.4 is just applying what we know about all our Chatelier and everybody else. Okay, let's move. Let us move to the next one. Write this down quickly. Okay, I need to mute someone here. All right, that's just one down, guys. I'm just gonna look for the person who wanted to ask a question. And as hopefully their name is like that on the group. I don't know which group is that, Vele, because there are 3 groups. Who's that? Okay, the one who wants to ask a question, right? All you simply need to do is go on your, if you're using a phone, let me just take you through the process. If you're using a phone, so I'm going to use my phone here. I'm going to go where it's written more, right? Where it's written more right there. And then from more, I can be able to say raise my hand, right? Raise my hand. Where there's more, I can be able to say raise my hand. Right, let me just get down to the other guys that got their hands up. Let me ask Nana. There you are. Go ahead.
Sir, can you hear me?
Yebo.
Can you please explain again the table? I don't understand. I'm lost.
Yeah, lost. No problem. Let me just get the next question, then I'll come through to you. Otherwise, allow me to do this, Nick. Allow me to go through everything. Then I'll come back to the table. I want to give other people something to do in the meantime, okay? I want to give other people something to do. But allow me to go through the other questions. Then I'll come back to the table now. Please, right. Allow me to do that. Don't worry, I got your back. I'll explain this again over and over again until you understand. Okay, guys, let's go further on this one. 6.3, I'm ready. The diagram below shows the reaction mixture in the gas range after equilibrium is established. The pressure is now increased by decreasing the volume of the gas range. Please don't forget that. The pressure is increased by decreasing the volume of the gas range at constant temperature as illustrated in the diagram below. And you've got a diagram that shows, like, you know, when you're increasing pressure, what you do to volumes, like that plunger, you push it inside. That means the volume decreases. And when the volume decreases, the pressure will increase. 6.31, immediately after increasing the pressure, the color of the reaction mixture in the gas syringe appears darker than before. Give a reason for this particular observation. Give a reason for the observation. Why, in this case, the color of the reaction mixture in the gas syringe appears to be darker than before. Let's do some logic. Let me help you. Okay, let me help you on this one. Right, guys, how many moles do you have on the left-hand side? You got 2. Work with me. You got 2. And on the right-hand side, you've got 1. So let me go 2 and then 1. What did we do to pressure? What did we do to pressure? We increased pressure. What should happen? There must be a decrease in the pressure. That's what should happen. There must be a decrease in the pressure. And decrease means coming from big number to small number. Right. But I want you to understand what's really going on here. It says here, immediately after increasing the pressure, the color of the reaction mixture in the gas syringe appears darker than before. And then the question is, give a reason for the observation. Now, I want you to get this. What made the color of the mixture to become darker than before is because there was an increase in the concentration of the gases. And let me go back. Listen to the question. That's why they put immediately in capital letters. So you might understand that it's not a direct result of the pressure that was changed, but rather a direct result of something else. And let me just explain. Let me read again. Immediately, capital letters, I'm reading, right? It says, immediately after increasing the pressure, the color of the reaction mixture in the gas syringe appears darker than before. Give a reason for this particular observation. Guys, when you go back to rates of reaction, when you increase pressure, you increase the rate of any reaction. The reaction rate moves faster, right? So in this case, because there was an increase in the pressure, we expect that the reaction rate moves faster. And therefore, the molecules are more compressed, they're closer together. The molecules are closer together, they are more condensed and move closer to each other. And then that means the rates increase. In this particular case, the rate immediately after increasing the pressure, there's going to be an increase in the rate of the reaction. And then at the end of the day, you're going to have a situation where it's not necessarily going to be colorless. It's not a clear color of one color of colorless, but rather it's a mixture of the two. It becomes a bit darkinyana here and there. So it's not really dark brown on its own, neither is it colorless on its own, but the fact that both reaction rates are increasing by virtue of increasing the pressure, it will help. I'm going to give to the next person, got their hand up, ask me. I'm going to come back to this. Listen to me immediately. Go ahead.
Sir, can you hear me?
Yebo.
I wanted to ask, okay, by the way, it was me that wanted to ask a question. I just didn't know how to ask it like with the laptop. But anyway, I wanted to ask, in this question that you've just done, you immediately, because we're working backwards, you immediately was like you were able to just take the 171 and equate it to the 2, right? But like, because one of them is a gas, you were able to put in the digits there. Are you
both of them are gases. Yeah,
sorry?
Both are gases. Both are gases.
Yeah, yes, both of them are gases, but like there was a previous question, the one we did before this one, how come you are not able to, because that one only was composed of like, I think there was a solid and there was one gas, so automatically the solid would be 1. So yeah, so why didn't you like equate the Kc value that we were given, the 1.2 times 10 to the power of -4, and equate that to the gas, which was going to be in the denominator because it's a product, and then the solid would have been 1. So if you like ended up equating it together, couldn't you just say that the concentration of that ammonia, or whichever it was, the products, because one of the products was actually a gas, couldn't we say that the concentration would have been equal to that 1.2 since the denominator is 1. And, you know, I don't know if you understand what I'm saying, because you did it in the second
I
one.
understand. That's what I did.
Yeah. Is that what you did?
That's exactly. Look at it. KC, there were 2 gases, not 1. There were 2 gases.
Yeah.
And those were products. So
Yeah.
then the KC becomes the concentration of the ratio of the product, which is those 2 gases. That was ammonia, NH3, and H2S, the 2 of them.
If there are 2 gases, do you divide by 2 or something, or it's the concentration
No, you don't.
of each of them?
You take them as they are.
Okay.
No, you don't divide by 2. You take them as they are, and their powers, and their coefficient powers. Everyone had a coefficient of 1 is to 1. So in that case, it was easy. It was going to be just NH3 multiplied by concentration of H2S. That's all. That's what I did. I combined both of them.
Okay.
Right? Did you see what I just did? Yeah. That's why I like the way you're thinking about the fact that the denominator must be 1. But you don't take one gas, you take both of them, because those are the products at the end of the day, together with their coefficients.
Okay.
You get that?
Okay, so
beautiful. All right.
Like even the previous question. So even the previous question, like it's fine the way you did it. And if we attempt other questions that are related to this one, where you have to like calculate for the initial and stuff like that, the initial number of moles that were there.
Go back one. Mm-hmm.
Okay.
Yeah, we do that. All right. Okay. Thank you so much for that.
No problem.
You're welcome.
Bye.
All right. Sharp. All right. Let's go further. Thank you for that. Let's move, people. So I was saying to you guys, for 6.31, the answer, right? The following: concentration of the gases increases, or rather say, I don't like saying concentration of the gases. Let's say, write the following now: molecules become more compressed. There was a decrease in there was an increase in pressure. Molecules become more compressed or move closer to one another. Molecules become more compressed. Remember, you're at equilibrium. You've got your dark gas and your colorless gas. So now they're going to be compressed and now move closer to each other. I hope you understand this. Guys, now I'm a gas. Because at equilibrium, you've got dark brown and colorless gas. So now because you've pushed the plunger together, so it was a separation of the colorless gas and the dark brown. So now that you've moved together now, they become quite closer. They move closer to one another. So the answer is molecules become more compressed or they move closer to one another. That's why there's that dark brown kind of color, or that darkish color that is formed, because now the molecules move closer together. Okay, I'm going to attend to the messages now. Follow me, please. Let me go to 6.32. Let's explain. After a while, okay, remember that was immediately. That one when it was having that darker color. Now, after a while, remember, and I want you guys to understand what's going on in chemical equilibrium. When you mess up, when you disturb an equilibrium, the system shifts itself. It needs time. You disturbed it by increasing pressure. So it needs time to shift itself, and then after some time, it will re-establish its equilibrium. It will go back to what it was. And for it to go back to what it was, it needs to favor a reaction which opposes what you did. So it needs to favor a reaction which counteracts the disturbance. All right, let's go ahead. Let me help you out on this one. It says to me, after a while, a new equilibrium is established as illustrated below. The color of the reaction mixture in the gas now appears lighter than the initial color. 6.32. Use Lee-Chatelier's principle to explain the color change observed in the gas range. Work with me. So your moles are 2 and 1. You increase the pressure. You must look for a reaction which decreases pressure. To decrease means to move from 2, big number, to 1, small number. You're going forward. And when you're going forward, your color becomes lighter because you're moving from dark brown to colorless. That's what happens when you go forward, moving from dark brown to colorless. So they want you to explain, according to Lee-Chatelier's principle, why at the end of the day, the color change becomes a bit, it becomes a bit lighter. It's because eventually you favor the forward reaction. That disturbance in pressure, which was an increase in pressure, must make sure that there's a decrease in pressure To decrease pressure means to move from big number 2 to small number 1. Forward reaction. What color change happens when I'm coming to forward reaction? I'm moving from dark brown to colorless. And that becomes your answer right there. So we need to explain that using Chatelier. Why now the color is a bit lighter after some time when we have established a new equilibrium. Okay, I see messages here. Let me just read them. Then I just read the answer for you. Okay, thank you. All right, I'm reading. Here's the answer. Try this. I'm coming to you. 6.32. Increase in pressure favors the reaction. Increase in pressure favors the reaction that leads to a smaller number of moles, smaller number of gas moles. Let me say gas moles. Increase in pressure favors the reaction that leads to a smaller number of gas moles. That is from 2 to 1, right? From 2 to 1. That is from 2 to 1. Full stop. That is from 2 to 1. Full stop. Then you go and say the forward reaction is favored. That is from 2 to 1. Full stop. The forward reaction is favored. Forward reaction is favored. Forward reaction is favored. That's fine. So you can write that forward reaction is favored and take it up from there. Snellkanta, go ahead.
So I wanted to ask, the statement that said molecules become more compressed, was that for 6.3.1?
Yeah. Because remember, when you decrease volume, molecules of the darker gas and molecules of the colorless gas. They become more compressed, they come closer. They mix, they move closer. So now there's a mixture of colors, colorless, net dark brown, once you've just increased the pressure by decreasing volume. It's like you're pushing guys close together. Like I'm a yellow bone, I'm a light bone. I'm a dark bone. So the color is a mixture. At the same time, but confused. All right, 6.41. There you are. Let's go. Okay, 6.41 people, I got your back. Okay, Nomvelo, I want to give you a hand. Nomvelo, ask me quickly. You never asked me in class. Oh, that's nice.
I do.
Oh, Nomvelo.
In 6.3.1, you said it becomes more compressed, right?
Right.
So that's before the new equilibrium is reinstated.
Yes,
okay.
That's before the new equilibrium is reinstated. Exactly.
Okay.
It becomes more compressed. Thank you, Nomvelo. 6.41, I'm reading quickly. The temperature of the mixture is now increased and a new equilibrium is established. How will each of the following be affected? Color of the reaction mixture. Then the next one is value of Kc. All right, let's discuss it together as a family. Okay, what did we do to the temperature? We increased it. Now, look at the reaction at the top. Delta H is less than 0. Delta H is less than 0. That means forward is exothermic and backward is endothermic. An increase in temperature favors endothermic. Endo is backward. Endo is backward. So what is the color there? Will it be darker, lighter, or remains the same? Write it down right there. I need to see people what I'm talking about. Darker, lighter, or remains the same? Write it down on the chart there. Let me see the answers there. Darker. Somebody saying darker? What do you think? Darker. Yes, it's because I need to, guys, by increasing temperature, you are favoring endo, and the endo is the backward reaction. Backward is from colorless to dark brown. So it's definitely darker. Thank you so much, guys. Write it down. It's darker. 6.41. Let's go to 6.42. 6.42. Let's go to 6.42 quickly so that we can get it done nicely. 6.42. Tell me something about Kc. Aha. Kc. So let's break it down. My people, this increase in temperature is favoring the backward reaction. So what does that do to Kc? Remember, Kc is only affected by temperature. So in this case, because you increased temperature and you favor it backward, that means Kc decreases. How do I know this? How do I know this? When I favor backward, I'm making more reactants than products. So Kc decreases. Kc decreases. So every time you favor backward, whenever you change temperature, listen to the statement. I'm going to combine it. Whenever you change temperature, how so in this case, increasing temperature, and then end up favoring it backward, it means because you increase temperature and favored backward, Kc decreases. Why say? It's because you're making more reactants than products. Every time you change temperature, favor backward, Kc decreases, more reactants than products are made. So the answer for 6,42 is decreases. Decreases. Beautiful. Right. Now I want to make sure that I get down to my next question. Okay, somebody else had asked me about the table. One more time, I'll explain it. But before I explain the table, just want to give something to people to be able to do this. Guys, right. I'm gonna screenshot, I'm gonna show you this. Can you please screenshot it? Because I want to go back and explain the table. So I can't do that while I'm still sharing the screen with the question that I want you to do. So if those that are using the laptop, you can also screenshot on your laptop, or you can take a picture using your phone. Doesn't really matter. Screenshot what I'm going to show you now. I'm going to stop sharing now. Let me see this. Stop sharing. Then please screenshot the following, because I want to show you what is your next thing to do. Screenshot it quickly, guys. There you are. Let me see which question I want. Let me see. This one. Yeah. Screenshot this. Screenshot this quickly. Screenshot. Right? Then you start doing it. Then I'm going to explain that question that one of you had asked me quickly now. Screenshot, guys. Then if you understood that previous one, everything with the table, start doing this one now. You got about 7 minutes. I'm going back to the table, so I need to share the table as well. Right. So those that understood that one, please go through this now. Screenshot that one more time, guys. I'm waiting for you. I'm going to give you 30 more seconds for the screenshotting. All right, screenshot. Start doing. Right, guys, this is a 2017 June paper. 2017 June paper. It's actually 2017 Senior Certificate June, right? Or just write 2017 Senior Certificate Paper 2, Question 7. 2017 Senior Certificate Paper 2, Question 7. All right, sharp. Let me explain. I'm going to stop sharing this one, then I'm going to go back to that other one. All right, in the meantime, work. Okay, somebody asked me, I want to explain the table one more time so that everyone can understand what I'm talking about. Let's go back to the table. Ntavi Seng, Jaka, I'm going to unmute you. Please, go ahead. Ntavi Seng, I've unmuted you. Try that again. Oh my word. I think your network is bad.
Sir.
Yeah, bo.
Can you hear me now?
Yeah.
So I have this problem when it's come to the table. Ne? Sometimes when you read, they give you that at equilibrium, maybe N2O is equal to 0.4 moles. Ne? Then you take that 0.4 moles and substitute on maybe substitute a good concentration, but sometimes utata 0.4 substitute a good moles at equilibrium. How do I know if butter at equilibrium it's 0.4? Do I substitute on E concentration or moles at equilibrium?
No problem. Thank you so much, Ntavi Seng, for that. Listen, it's when they say 0.4 moles, right? At equilibrium, there was 0.4 moles. You go to moles at equilibrium, right? Moles at equilibrium. If they say 0.4 moles per decimeter cubed, that's concentration. It's about units. And Moles per decimeter cubed, that's concentration, units. So you go to concentration. So the fundamental difference is the following. Let me write it down for you right here. My man, 9. La ama moles. You put it to moles only, moles at equilibrium. Lena, this is the unit for concentration. This one, there. So the report is that the difference between saying 0, there's a difference between saying 0,4 moles and 0,4 moles per decimeter cubed. This stands for concentration. This one. That one stands for moles. We are told.
Yes, thank you so much.
All right, you're welcome. Okay, let me go back to the table one more time, people. While
yes, sir. Yes.
Okay, sharp. I'm going to the table now. So, guys, I was saying on the table there, and it's 6.2 on that question. At equilibrium, the concentration of NO2 is 0,2 moles per decimeter cubed. The Kc for the reaction is what you see there. All right. Ntavi saying, another Ntavi saying, yay, nigcwele lapha. Yo, yibobota. Right. I'm gonna unmute you. Maybe you can, so that you can just answer what you need to hear. Right, quickly. Yeah, one Ntavi saying. Hello.
Can you hear me?
Yebo, ngiyakuzwa network, ngiyakuzwa.
Yes. I think what Untabi saying Jatla was trying to ask ne. Katebuza uti well, let's say maybe the initial moles they gave you 0,4.
Ntabi saying, I think you've disappeared. Could be network. Could be network. Okay, I'm not really winning with her. Can someone send the screenshot to the group? I think Uzinhle is getting a bit confused as to what we're doing. Can someone send a screenshot to the group, please? We're doing the question on the screenshot. I ask people to, yes, count your back. Yebo, go ahead.
Yes. Can you hear me now?
Yebo.
I think Untamseng was trying to ask about, let's say initially they gave you 0,4, right?
Mm-hmm.
Can you hear me now? Yes. And then let's say the concentration azanke baknikezele, and then the concentration baknikezile, and then the initial mole baknikezile. Now you need to get the moles at equilibrium. Can you hear me?
Yes.
Yes. So are you going to substitute the moles initially on the moles that are used and moles that are at equilibrium the same?
No. I hear you now. No, you only substitute the moles at equilibrium. In fact, you know what? Predominantly, if you look at this question that I'm trying to explain now, predominantly, you're going to be using this formula, right? And then C, concentration at equilibrium, is equal to N, number of moles at equilibrium, not at start, at equilibrium. Because at start you had something, then you used it or produced it along the way. So you use the number of moles at equilibrium and the volume. So you don't use the number of moles at start, you don't use the number of moles used to produce, you use the number of moles that I have at equilibrium. Is that okay?
Yeah, I was just clarifying her questions.
Okay, you did well. One type is saying for another type is saying. Thank you, much appreciated. All right, let's go to our next one. I'm just trying to still explain this to you. Can you mute yourself? Thank you. So guys, I was saying the ratio is 2:1. Let me just go quickly on that because I want us to make sure that the next question that you guys are doing, you get it. Other people are probably done with it. 2:1. And then I didn't know the moles of NO2 and I call it X. The ones for N2O4, I call it 0. I was given Kc, which is 171, and its concentration of the reactant or product over reactant. And then concentration A, NO2 is 0,2. Just cross multiply, squared. Remember that it's according to the stoichiometric coefficients, the balanced equation. Okay, so I square it. Then I cross multiply on that one, I square it. And then after that, I get the concentration is 6,84. What Untabi is saying was asking me now is, okay, now that I've got 6,84 as my concentration of N2O4, how do I get this number here? There, C is called N over V. And then you can see for yourself there that C 6,84, N, V 80 divided by 1,000. That's 80 cubic centimeters. That was the volume divided by 1,000. And that becomes 0,5472, like that. And then in the beginning, you had 0, and at equilibrium, you got 0,5472. So you must have made 0,5472. Use ratios here. Use ratios to get this other number here, 1,094. Right? I use the ratios there. They are 1,094. But remember that from what they told me, the concentration of this guy, I had him 0,2. And then to find the number of moles, again, type of things question comes through again, 0,016 moles, right? Concentration times volume is moles. I get this number. Then for me, it becomes easier. X is what I had in the beginning. Let's do some sense. I had X in the beginning, and then I used 1,0944. Then I have 0,016. So math will say X, what you had minus what you used, is equal to what you have. Or rather, think about what happens to the guys that I use. It's always X minus this is equal to that. Remember, products you add, but reactants you subtract. X minus 1,0944 is equal to 0,016. That's what I put right there, and then 1,11. It's all a matter of following the steps as we've always done before. It's nothing out of the ordinary. That's just following the steps right there. Okay, right. I'm hoping that people are winning. I'm on the next question. Okay. Okay, iPhone, your hand is raised up. I'm going to attend to you now. Go ahead.
Sir, can you hear me?
Yeah.
I said, is there a difference between nitrogen monoxide and nitrogen oxide?
No, there's no difference. Nitrogen monoxide means NO, something with one oxygen, or nitrogen oxide, something with one oxygen. It's the same thing. All right, thank you. All right. Okay, guys, finish up. Okay, now I'm going to share the question. I'm going to share the question now. I'm going to share it now, quickly. Where is it? I'm going to screenshot. No, not screenshot. There we are. Where am I? There. Okay. Sinclair, that's what we're doing. Sinclair, that's what we're doing right now. Two more minutes, guys. Then we do this question together. 2 more minutes. Please screenshot this. Whoever has not screenshot this, please screenshot it, because I want to go out. I want to stop sharing because I want to do something quickly here. So please screenshot it. Giving you 10 seconds. Screenshot this. There. Okay. Canceling it out. One more minute. One more. All right, let's do this together, guys, as a family. Let's do this together as a family. Let's see how it goes. Just to make sure that everything is fine and clear up. My system is loading here. Okay, let's see how far that goes. There we are. I'm going to go back to the question, the one that we screenshot, just to make sure that everyone is clear up right here. Right, that's the question that we're doing. Right. Okay, guys, I know initially I told you that it's a 2017 senior certificate. It's actually not, right? I think it's, let me see where it is from. It's Free State, 2017 Free State prelim. That was my mistake right there. 2017 Free State prelim, paper 2, question 7. And I want us to go through that one very quickly. All right, there we are. Okay, right, let me just screenshot it myself here so that at least I have it there. Okay, I'm reading. It says, consider the reversible reaction represented by the following balanced equation. NO, 2NO, everyone is a gas, O2, and then 2NO2. During this reaction, 4 moles of nitrogen monoxide gas, 2.5 moles of oxygen, and X moles of nitrogen dioxide are placed in 500 cubic centimeters container at a temperature of 450 K. At equilibrium, there's 3 moles of nitrogen oxide, which is NO, present in the container. Okay, that's why iPhone was asking me that. The Kc is 0.25, 7.1. That's what you have. Okay, for the sake of our time, what is X? Let me see what you got. What is X? Write it down. Write it down there. And I want to see it on the chart. Write it down. Then we can confirm together. What is X? Hey, people are afraid to write X. 2. Can I get a 2? Sandra says 2. Anybody else got a 2? Okay, let's do it together. Let's do it together. Let's see how far we can go. Right. I'm going to go to the whiteboard now. Share the whiteboard quickly. 1,995. I got 4. Winning lotto numbers. So nama lotto numbers, Lana. 5, 4, 7, 25, 39, whatever the numbers are. Let's confirm this together as a family. Let's see how far we can go. I'm ready. Let's go. Okay. I need to go to my screenshots because I need to see this question myself because I have not done it. I'm going to be doing it with you just now. All right. There. So I need to write my table. I need to put everything on my table quickly. 7 marks. So that's MR, the Molar Ratio. It start, okay, moles is start. I think you guys know this by now. Used or produced. So I'm going to have this as used or produced. Okay, used or produced at equilibrium. At equilibrium, those are moles. Don't forget. Then you got concentration at equilibrium. Okay, let's break it down together. Let's see. We got 3 guys in this mix. You will help me out with the maths because I'm really not using a calculator, so I wouldn't really know. So there you are, and then there you are, and then there you are, and then there you are right there. All right, beautiful. There you are, 1, and then I'm gonna put this as my second one, and that's fine. So I think from what I'm looking at right here, on my particular picture that I screened, I've got NO, nitrogen monoxide or nitrogen oxide, and then I've got O2, then I've got nitrogen dioxide. And the ratio is 2 is to 1 is to 2 moles of start. During this reaction, 4 moles of nitrogen monoxide in the beginning, and 2.5 moles of oxygen, 2.5, and of moles and X moles of nitrogen dioxide are placed. So already I have this guy. He's not 0, he's X. And X moles of nitrogen dioxide are placed in 500 cubic centimeters at a temperature of 450 K. And then at equilibrium, there's 3 moles of nitrogen, 3 moles. What Untitled is saying was asking me, guys, it's 3 moles at equilibrium there. 3 moles of nitrogen monoxide. Let me just make sure that I'm looking at the clear thing. Yes, nitrogen oxide or nitrogen monoxide. Kc is 0.25. I do the math. Let's start here. So if in the beginning I had 4, and then at equilibrium I have 3, I must have used 1. That's fine, right? I must have used 1. There, 4 minus 1 is 3, because this guy I'm using him is my reactant. This guy I'm using him. This guy I'm making him is my product. So I want to fill up the table nicely, right? And then if I do the ratios now, I want to do ratios here. If I compare nitrogen oxide with oxygen, the ratio is 2:1, and I've got the moles there of nitrogen oxide, which is 1, and then this one I'll call it X right there. Cross multiply, 2X is equal to 1, and then X is equal to 0.5. So here I'll put 0.5. Remember, guys, on step number 3, use ratios. So I had 2.5 in the beginning. I used 0.5. So here I'm going to have it as 2. That's what I have right there as 2. Then I'm going to go again ratios. 1 mole of that. I don't know how many moles of that, but I look at the ratio, 2:2. So if it's 2:2, it's easy. You write the number as it is, 1. But this one is my product, so I'm making it. So this becomes X plus 1. X plus 1. And then I notice that now I can get my, my Kc, right? Or my concentration at equilibrium. Remember, concentration is number of moles over volume. So in this case, it's going to be 3 divided by 0.5. Because you have it as 500 cubic centimeters. Divide that by 1,000, that becomes 0.5. So Nklahla, I'm unmuting you.
Sir, I wanted to ask, Gandhi, aren't we supposed to times everything by the moles of nitrogen monoxide? The ones at equilibrium.
No. It's the one that you used. The one at equilibrium is after the reaction has happened. It's the one that you used. The ratios, okay, I hear you. The ratios don't happen here. No, they don't. No, they happen here. Right there. I need on step number 3. That's where you got your ratios. Because you're saying I used 1 of nitrogen monoxide with 0.5 of oxygen to make 1 of nitrogen dioxide. That's what you're doing. So you use that only at you only use ratios on step number 3 when it's used or produced. That's all.
Okay, so thank you.
Beautiful. So now I'm saying to you guys, now because it's this one is a product X plus 1, 2 there, after subtracting, subtract, add. And then now here, I'm going to come to concentration. Guys, remember, concentration, number of moles over volume. The number of moles is 3. The volume is 0.5. Because remember, it's 500 divided by 1,000. So volume is 0.5. So 3 divided by 0.5, I think it's 6. And then 2 divided by 0.5 should be 4. This one becomes X plus 1 over 0.5. You are given Kc. Sandiswa, I'm coming to you. You're given Kc as concentration of the product, NO2, and it's squared over concentration of reactant, which is now NO right there. And I'm writing the expression. You get a mark for this, squared. And then you get that as well, O2. And that O2 is to the power 1. Kc, I'm looking at my screenshot now. Kc is equal to 0.25. Please help me with the maths. 0.25 is equal to NO2, there we are, squared, because this one is my product, right? And I've got the concentration of NO at equilibrium, which is equal to 6 squared multiplied by oxygen, which is 4. Guys, please cross multiply this for me, then get me my NO2 after square rooting. Don't forget to square it. Then get me my NO2 concentration. All right, Sandisa, as a boy. Right? So I want to make sure that I get this right. Please write it down for me on the group, on the chat there. Put on the group, on the chat. Just want to see what answer you get, so that then I can do the maths. 6. I hear 6. Thank you. So I'm going to write this as equal to 6. All right. So that's 6 right there. Guys, please avoid doing this. I know you. You want to say NO2 Lana, you take that X plus 0.1 divided by 0.5 and then put it there and you square it. Then you end up having a quadratic equation. You're going to stress your life. So rather Go with it until here. Then remember that this guy, NO2, is the one that is equal to x plus 0,1 over 0,5 is equal to 6. Now I can multiply. Now I can get my x. And if I cross multiply here, what is 6 times 0,5? 6 times 0,5? I think that's 3, right? All right. And then x, so it's x plus 0,1. 6 times half, that's 3. Then you're looking for x at the end of the day. X is equal to 3 minus 0,1. What do you get? Come on, come on. Am I doing the right thing? What did I do with my maths here? That is wrong. Okay, I see the hands. I think I did some maths which is wrong. I don't have a calculator here. All right, iPhone, there, talk to me.
So where did you get the 0,1?
Oh, it's 1. Ish, guys, look at 0,1. All right, it's 1. There. That becomes 3. That becomes 2 then. X is 2. Yeah. X becomes 2. All right, there you are. 1, X becomes 2. I think everybody else wanted to shout at me for that. That's why all your hands are like, yay. Let me lower them down. If you want to say something, if it's something that is related to something else, all right. I think Sandy, so you had your head up before that thing and all that. Can you please lift it up again? I unmuted you. Lift it up again, Sandy. All right. There. Go ahead, my man.
Hello, sir. Can you hear me?
Yeah.
Okay, sir. I wanted to ask, where did you get the one in the used or formed for NO2, the product?
I used ratio. You see, if I compare, let me write it here. If I compare NO to NO2, the ratio is 2 is to 2. And I know this guy. Remember, I know him. He's the first guy that I found. Yeah, that's how you
it's
get
like NO. Okay, I get it, sir. Okay.
When the ratio is 2 is to 2, you just take that number as it is.
Okay.
All right. Yogi,
okay,
I'm going to unmute you. All right, Sandy, sir. Thanks, man. Yogi, I'm unmuting you guys. We're done. This is our last question. I'm not going to go further after this. Yogi, go ahead.
Sir,
yeah.
Is 1,95 as the answer correct? Is it fine if I got the answer as 1,95 instead of 2?
How did you get it as 1,9? Because this one will give you direct mathematics. Like the numbers are very clear. Or unless on when you say 0,25 times 6 squared times 4, do you get a direct answer, a clear-cut answer, or you get something that's...
No, sir.
You get what? You know, when you say 0,25 times 6 squared times 4, do you get a direct straight answer, or you get something with comma, comma, comma?
I got a 36, sir.
That's a direct number. Yes. So, 36, then you square root it. That becomes 6. No. You must get it as 2 exactly. Straight up as 2. Okay, go back and check it out. Maybe there's 1 or 2 mistakes that you made. Zanele?
Sir, I got 8. I don't know.
How? The answer is 2.
You know what I did, sir? I took 0,25 and I multiplied by 6 squared times 4.
Right, I agree.
And then I root it for that square root of nitrogen oxide. I root it and then I got 6.
Yes.
And I took 6 and say 6 plus 1 divided by 0,5 and I got
6. No. 6 is the concentration of your NO2. It's not the number of moles. It's concentration. So X represents the moles that start right there. So you can't take 6 as the concentration right there. Then you say plus 1. You need to change that 6 into moles. So you needed, if your method, you needed to change, say, okay, 6 is the concentration, number of moles over volume. So it's going to be 6 is equal to N over V, where V is 0,5. Then cross multiply. Then your N is 3, not 6. Then you go up and say 3. plus 1 at the top right there. Right, until eventually you get that. So you can't do that without by saying 6 is not the number of moles, it's the concentration.
Yes.
Right? You see that? Okay. Zandi?
Okay, so can you hear me?
Yeah.
Okay, I wanted to make sure back at the table. So you said we use the ratios at the third column, moles used or produced.
Yeah, all the time.
Oh, okay.
All right, beautiful. Okay, guys, I'm gonna stop sharing now, and then after this, I'm gonna just give one announcement, and then we end it up from there. All right, thank you so much for coming today. You guys were wonderful. I will send you a document, but I'm so busy this whole weekend and all that. I'm so busy, like no man's business. I will be able to send you another document maybe sometime next week to do with chemical equilibrium that you can try. More questions. The more you do, the more you know. I have a lot of these questions, so at least that way you can be guaranteed. Right, like I was saying in the morning, guys, on Sunday, I'm going to have another lesson, but the Sunday lesson is different from today because the Sunday lesson is paid for. I'm going to be doing mathematics, financial maths, and then for physics, I'm going to be doing electric circuits. Your worst nightmare is coming right at the door. So I put a poster for you guys to check. Then the other thing is this. I put a poster on the group. You'll check it out there. Then you inbox me if you are interested. Then the other thing is this. There's been an email that's been circulating about Star Schools. Hey, selected you, blah, 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 what. And people have been asking me about it. I don't know. So tomorrow when I'm at school, I'll get the information. Then I'll tell you what's happening with that one. Then for those that are not from Star Schools, thank you so much. That I will send you the handout. If you're not from Star Schools and you're here on the platform, and I think there's many of you, please send me a message on my WhatsApp. Then I will send you the document that we used for the first question. The first question, that document, I'll send it unto you. Then I'm going to send now a document on acids and bases that we're going to use tomorrow. That document is already printed. We're going to use it tomorrow for school. Start reading now. Tomorrow's lesson is long because I'm going to explain a lot of things. So start preparing yourself. I'm going to send that acids and base document just now so that everyone can have it and start preparing yourself. But I'm going to unmute you now. There you are. I'm going to unmute all of you to say hi and bye. Anguzwa?
Cela imemo.
Imemo ya yiphi topic?
Chemical equilibrium. Let's start again manje. Like the paper thingy.
For this question, right? I'll send this question to you guys. I'll send the memo to this question to you guys. Yo, but thank you so much. Kuno muntu ngathi nje uyandiza la ngathi nje in the middle of the day.
Baqalile baflying emithaneni, right?
Yo. Who's that? Yo.
Yeah,
okay, guys, listen. I'm hoping that you are really getting. I'm hoping that you're really getting the hang of the topic. Nyarasa. Okay. Let's start again. You want to say something, unmute yourself nicely. Don't unmute yourself when there's so much noise. Unmute yourself. Right. Let's talk.
So can I ask, was this lesson recorded?
It's on Facebook. It's live on Facebook. And I'm going to stop the streaming. So you're going to get it right there. I'm going to stop streaming right now.